Okay, moving on to viewing options for the digital aerial imagery. We have a range of different options. The system that we've purchased in-house is the planar monitor system, which is produced by Planar Co in the United States, and consists of two LCD monitors with a semi-silvered polarizing mirror in between, and the user wears a pair of polarizing glasses. One eye sees through the semi-silvered mirror to the image on the screen behind it, the other eye reflects off it and sees an image on the screen on the top. Okay. As part of the system setup, you can also use the software without the planar monitor, and you have the option to view the information on screen in anaglyph mode, which we've discussed before is using those red cyan glasses, and you can view it in side-by-side mode as well. This is an example of an anaglyph of ADS 40 imagery. This is from the Molong area, and as before, if you want to have a look at it quickly with your red cyan glasses, probably a good idea to have them by your side for the rest of these tutorials, because there's quite a number of three-dimensional images that are shown in anaglyph mode to give you examples of things. This is actually how the stereo analyst interfaces with ArcGIS to view the imagery. As I mentioned before when we showed you a swathe, this is the active image, the yellow band. The one alongside it in red is the inactive image of the image pair. Each image pair is made up of a nadir and a backward swathe, which is shown over here in the table of contents. And in the stereo window, the active swathe, which is this one on the left, is shown with north to one end of the image and south to the other end, not necessarily to the top of the window. If you look at the imagery over here, you'll see that in the selected swathe there's a bit of timber cover to the south and pasture to the north. Here's your timber cover, here's your pasture, so we can deduce that north is in this direction. It will align to the north in the ArcGIS window unless you set the properties up to align it to what's seen in the stereo window. You can also set it to follow what's in the stereo window. So that's what you'll see when you look at a three-dimensional imagery in the ArcGIS environment. This is a close-up of the same situation, only in this particular image set we've actually rectified some normal air photos, and you can see how they overlap, and they have the side and forward overlap. And this is the selected image pair here, which is showing the stereo window. This can be accomplished if you're doing time series analyses and require rectification of older aerial photo runs for legal cases and such, but it's time consuming and probably will become less and less of an issue over time, but in this particular case it's just an exemplification of what you can expect to receive should you require it. And if memory is correct, yeah, this is actually an anaglyph image that is what you will see in the stereo window, literally, if you're using it in anaglyph mode on a normal PC. These two windows down the bottom are not in stereo, the image at the top is, and these images are used to align the stereo model so that you get an easy on the eye model, if you want to think of it in that way. You'll see there's a tank here which has a red cross on it, same on this one, so they're both lined up over the same point in space. Here it shows in the main stereo window. If these things are misaligned, you can use the Z scroll wheel to adjust it so that they line up over the same point in space, and that will give you the optimum stereoscopic model in the stereo window. They can actually be turned off. This icon turns them on, these bottom windows. This icon gets rid of them and puts it back to a full stereoscopic image, and this icon will create a split view that you can use with a stereoscopic viewer to see a three-dimensional image without being in anaglyph mode. And that basically is the viewing options component. Right. Okay, now let's talk about digital airborne imagery versus Spot 5. These three images detail three different products: ADS-40 on the left, Spot 5 in the middle, and a 1 to 50,000 scale colour aerial photograph on the right, all presented at roughly the same size on the screen. And you'll see that the ADS-40 is very similar to the 1 to 50,000 scale aerial photograph. You'll find that the Spot 5 in the centre is far more pixelated and blocky, more difficult to observe things in, and that's generally a result of the different pixel sizes. It's important to also realise that while Spot 5 records 2 infrared bands, it records a red, green and panchromatic. It doesn't record a blue band. It is limited by a 5 metre resolution panchromatic and a 10 metre resolution multispectral. There are products available to pan sharpen and such, and I think now we can get down to 2.5 metres resolution. But when you compare that to 0.2 to 0.8 of a metre resolution across all bands in the ADS-40, and that includes infrared, full red, green, blue and panchromatic, the ADS-40 is a far more useful product. But the Spot 5 is useful over large areas. It's being used more in the western part of New South Wales, where the sort of accuracy that and scale that ADS-40 can provide isn't so relevant. ADS-40 is being flown in those parts of the state where specific flyings are being requested, or for town areas or high value lands or specific jobs. Generally the ADS-40 is going to be restricted to the central and eastern parts of New South Wales. So this gives you a bit of an idea on the differences between ADS-40 and Spot 5. Okay, we'll move on to specifications and definitions of digital airborne imagery. And as I said before in a previous tutorial, the imagery comes in 3 formats: level 1, raw, and level 2. And as a result of that, what you'll see is a situation like this prevailing if you pull in 2 level 2 images, which, as I mentioned before, I produced for a full 100,000 scale map sheet in area. And you'll see that they are designed to join along the map sheet boundaries, and they are colour balanced across the image as best as possible. These are actually mosaic together from the individual swathes, which, as I said, run north-south, and they're cut together along boundaries to make them practically invisible. You should be aware that the location of the cuts to put these swathes together as a mosaic is held by the department, and can be important if we're looking at flyings on different dates and you're looking at compliance cases and such. So be aware that these swathes can actually be flown at different dates, not necessarily on the same day depending on weather conditions. So as a result you might find that either side of a cut line is a completely different date. Okay, so as I've said, these are both 1 to 100,000 scale map sheet areas, and we'll move on to georeferencing orthorectification. This is an important demarcation, one that you should have some understanding of if you're going to be talking about the different spatial products. Georeferencing is a system where imagery is aligned to its correct location on the Earth in terms of latitude and longitude, and enables it to be displayed accurately in location to maps and coordinate systems, and it can be a 3D product. Okay, this definition that's on the screen has been adapted from various sources. The important difference between that and orthorectification is that georeferencing is a rubber sheeting or stretching of an image to align it with no coordinates. There's no elevation models used, and the points on the image that are actually realigned doesn't mean that anywhere between those points is accurately aligned to the correct position on the ground. That is, the scale is not necessarily uniform between one point and another. So you could find areas between points that have actually been accurately located that are in fact not accurately located. The term rubber sheeting is a good way to visualise what's actually going on. Orthorectification is a different process, where each particular point on the ground is aligned to its correct spatial location in terms of x and y, and it's projected to a plane. A two-dimensional image is the result, and that two-dimensional image is able to be aligned exactly with that maps, so accurate measurements can be made. And the important difference between that and georeferencing is that the scale is consistent across the image, and that any point on the image can be observed in its true location in space. For the terms of ADS 40, the imagery in the stereo window is georeferenced. It tends to align correctly over other georeferenced information presented in 3D in that window, but the actual swathes themselves will not align correctly in the normal ArcGIS window with the real world and with maps. Be aware that you need to have the level 2 image loaded in the ArcGIS window if you intend to create map accurate data or compare it to map accurate data. Okay. Let's talk a bit about the planar system and how it deals with these things. As I mentioned before, the two monitors are separated by a semi-silvered polarizing mirror, and in this situation you can see that the right eye sees imagery from the top monitor because it reflects off the mirror. The left eye sees through the mirror and sees the imagery from the backward behind the mirror monitor, and the function of the planar system that achieves this is the flipper card, which is actually fitted into the computer, which inverts and reverses the top image on the top monitor. But importantly, it also changes the image inside the stereo window on the top monitor, so that what you're seeing is a left eye, right eye view inside the stereo window on the two monitors. So the only part of the screen that is different is the actual stereo window. On one monitor, the left eye window, it will be either nadir or backward, and on the right eye in the top monitor, it'll either be the opposite. Whichever the lower monitor shows, the upper monitor will show the other sensor. This is how it looks in sort of viewing straight on. This is a full screen stereo image. You'll see that it's mirror reversed in the top from the bottom, and that when you're viewing it from an elevated position, you'll actually see a full screen stereo image. This is a good system for multiple users, as it can be viewed in an ambient light environment. There's no flickering involved, and it can be used for long periods of time without eye strain. There's a range of monitors available. The department has purchased SD2020s and SD26s, and I think the lower 17-inch monitors have now been discontinued. Okay, we'll just leave it there for the time being, and we'll come back later to talk about specifications and more about the planar system. Okay, let's move on to some ADS 40 nuts and bolts, shall we? This is a bit of detail about the sensor that may put it into context for you. The sensor is a fairly substantial unit. These red lines in the image actually are big grab handles to lift the 200 or 300 kilos of unit into and out of the plane. There's a large mass memory unit into which feeds the inertial motion information, which comes from the position and attitude system. There's a gyroscopically stabilised mount that the camera sits onto, and there's a GPS unit integrated into the control unit. The operator has an interface in front of him, and the pilot has a monitor in his cockpit which shows him where the plane is in space and what's going on with the system. The calibration is flown prior to the collection of any data set, where the plane flies a test series of imagery, and you'll notice that the turns in between runs are fairly wide, and this is done so as to make sure that the GPS unit does in fact retain a good fix on the satellites. The more satellites it can pick up, the more accurate is its location in space, and the system is calibrated prior to the starting of any particular data collection exercise. The inertial motion unit basically senses any sideways or up and down or skewing movements of the plane, and converts that, correlates that to GPS GPS data input from the GPS sensor to correct for the plane's travel through the air. The workflow of the old film-based systems is detailed in the top part of this image. Basically, whatever you loaded into the camera so far as film was concerned was what you got at the other end. Went through a film processing wet lab situation, produced your prints and plots. Those could then be scanned. The negative image, actually a slide image or DAI positive, could be scanned at the finest resolution possible, or it could be sent to a stereo plotter, and orthophotos, mapping and other products can be produced, or it can be put through a GIS system. The digital workflow of an ADS-40, all the spectral channels are captured simultaneously, you remember from the earlier tutorials, goes through the mass memory unit, everything including inertial motion unit, GPS data and such comes through ground processing. This is fed through to a digital workstation. Data can be archived, printed or sent forward for further image analysis, and this process from downloading from the mass memory unit to a final usable product can be a matter of hours as opposed to days or weeks, which was the situation previously with the film-based imagery. The level 1 imagery, the image data and the orientation data, that is the GPS and inertial motion unit data, are fed through a rectification process. Orientation data can be then passed on to subsequent processes, and the image data, level 1 image data, comes out to a digital processing workstation and is stereo viewable. The level 2 data, same information is throughput from the system. It's overlain over a digital terrain model, and that produces the level 2 image by extracting the height from the image and projecting it to a planar surface. So it's a 2D ortho. The mosaic can be then constructed by joining the swathes, intercutting them and colour balancing them to produce a final orthophoto output map, or orthophotograph, or ortho image. Here's an example of a pre-corrected and post-corrected section of imagery. You'll see on the left that there's been quite substantial movement of the aircraft as it's flown along this particular swathe, and on the right the inertial motion unit and GPS sensor calibrations have been entered into the data set and extracted from the actual raw imagery to remove those perturbations in the actual image to produce an accurate series of images of that particular area. Right, let's talk briefly about Lidar while we're here. And the Lidar is a different sensor type. It's basically a sensor that fires out a multitude of laser beams from the sensor, hits the landscape, is reflected back to the sensor's receiver, and you get a location of a point in space and also some information about that point coming back to you. This image here has been coalesced into a range of different layers. Each layer is 20 centimetres apart from the other layers, and it grades through from yellow through to blue. Blue being the highest land here, and yellow being the lowest, as you can see alongside this watercourse on the map sheet that's actually in behind the data. This took ages to set up in the system. And there are far better products around to enable this information to be displayed. For example, move on to, before I do, you can see there's a double density of points through this area here. You can see there's some points here and the same sort of density points here, but a double density between. This is where two runs of Lidar imagery have overlapped, resulting in double density of information. Just move on to specialist software, and this is actually a product called LP360, which is produced by Q Coherent, and it's actually an area near Port Macquarie. The subset image on the right here is a view from the plane location out here looking onto the coast, and you can see it's being toned in terms of elevation. The high points red, the low points blue, and greens and yellows and such in between. you see in the main part of the image that you can see a basic outline of streets and such, which is part of Port Macquarie, but you can see the terrain has been isolated from that by extraction of the buildings and such. So this is actually a terrain model, not a surface model. A surface model includes all the buildings and such. The terrain model has just the surface of the ground, and this allows three-dimensional fly-throughs and such, and pulls the data in straight away from the basic LAS files, and it's a very useful tool to use for Lidar imagery. I'll move on to a usage example. This is actually an area out near the Macquarie Marshes in New South Wales. It's a property called Pillicawarra, which was purchased by the then Department of Environment and Climate Change, and it's quite flat, and Lidar imagery was flown across the area as part of a process of resource inventory to enable for good planning of the property and even environmental rehabilitation. You can see that this is a zoomed in view of that Lidar imagery. You can see the incredible detail that's able to be ascertained by looking at the Lidar, where it's picked up information from a road running through, there's a canal over here, you can see a watercourse running through here, and you can see a micro drainage structure coming through under the road and draining down to the waterway. There are areas of flatter land which perhaps have show signs of cultivation over time and filling in of the rills and little tiny watercourses and such, and areas which look like they haven't been disturbed very much by that sort of activity over time. So it's a very, very useful tool for this sort of analysis. Okay, that basically summarises the sections on Lidar and some nuts and bolts about the ADS-40. I hope that puts it into context a bit for you.